In 1927, Albert Einstein boarded a train to Solvay in Belgium. His journey would take him to the center of an argument between the greatest collection of scientists assembled this century. By the end of this conference, Einstein had lost a battle, and our understanding of the world had changed forever.
Quantum mechanics, in a nutshell, is the physics of the very small. Anything as small as an atom or smaller than that works in accordance with the rules of quantum physics.
And it's a very surprising discovery that the physical world at that scale is totally different in its behavior and character from the physical world of every day that we experience directly. The everyday world is clear and reliable. The quantum world, it turns out, is cloudy and fitful. So that was a big surprise.
Quantum physics has revolutionized our understanding of the world. The journey to the mysterious heart of the atom has forced scientists to take sides in a debate about the uncertain nature of matter, a debate that still continues today. It all began in 1897 when J.J. Thomson discovered that electricity was caused by the flow of tiny particles called electrons.
What Thomson decided was that he had found a subatomic particle which is a constituent of all matter.
And why is that important? Well, our entire understanding of matter today, normal, ordinary, garden variety matter, why grass is green, why the sky is blue, that understanding is based on how electrons interact inside of atoms.
Although Thomson and his colleagues understood the scientific importance of the electron, they didn't see any practical use for it.
Could anything at first sight seem more impractical than a body which is so small that its mass is an insignificant fraction of the mass of an atom of hydrogen?
They in fact had a toast at one of their annual dinners, which was, to the electron, may it be of no use whatsoever. Now, that's obviously very ironic because the understanding of the electron has led on to tremendous practical applications.
This pulling of electrons from atoms isn't done for amusement.
The electron particle was to make its first commercial impact in the cutthroat world of the American telephone industry. In 1907, the telephone was already 31 years old. AT&T, the company founded by Alexander Graham Bell, was facing stiff competition from thousands of smaller companies. The race was on to be the first operator to provide a long-distance service between the east and west coast of America.
The technology to do that didn't exist.
Can you recall the telephone of a generation ago? New York to Denver was the longest call that could be made.
The major technological problem that stood in the way of completing a long-distance line was amplification. As an electrical signal travels down a copper wire, it weakens. There's resistance in the copper wire. Eventually, it weakens to the point where there's no longer a usable signal. They needed a way to amplify the signal.
Desperate for a solution, AT&T invited anyone with an idea to contact them.
One person who did was an independent inventor named Lee DeForest. DeForest in 1906 had invented something called the Audion, the first three-element vacuum tube. He was using it primarily as a detector of radio waves, but he knew also that his device would provide a small amount of amplification.
But not nearly enough for AT&T. The Audion amplified the telephone signal by altering the flow of electricity between a metal plate and a wire surrounded by a vacuum. The problem was there was only a partial vacuum inside the Audion.
The space between the wire and plate is jam-packed with gyrating air atoms. And to reach the plate, the electrons would have to bump their way through them like midgets in a subway crowd.
The solution was to pump out more air. By doing this, the first useful electrical amplifier was born. AT&T used these high vacuum tubes to complete the transcontinental telephone line in 1914.
How much is your voice amplified by these repeater stations between New York and San Francisco? You say it. I can't. The figure is 10 with 99 zeros after it.
It was only made possible because of J.J. Thomson's earlier discovery that electricity was the flow of tiny particles, electrons. Theoretical physics had a commercial value after all. A lesson not lost on AT&T.
The transcontinental telephone line was an important step in knitting the nation together. The other effect it had was to firmly convince leadership at AT&T that bringing science in-house, hiring scientists, engaging them in doing research, was something that was a good business strategy.
They set up the Bell Telephone Laboratory. The high vacuum tube, or valve, became the workhorse of a new communications industry. Commercial radio and later television were made possible by the valve amplifier.
Yes, sir. If it weren't for these babies, there wouldn't be any radio.
At the same time, scientists were wrestling with radical new ideas about how electrons behaved.
At the end of the 19th century, it looked as though, essentially, we knew how the physical world behaved. There were the triumphs of Newton, which described how particles behaved, and gave you means of calculating what they would do. And then in the 19th century itself, the great achievement was Clerk Maxwell's theory of electromagnetism. That showed that light was a wave-like thing, waves of electromagnetic energy. And really these issues seemed to be settled, and many great physicists thought all that was left was just to tidy up the details, to dot the I's and cross the T's.
In the Victorian era, it seemed everything in the physical world was either a lumpy particle, like an electron, or a spread-out wave, like light. But in 1900, German physicist Max Planck saw there was a big problem with the wave theory of light. Planck was looking at the way light and heat radiates from hot bodies, like a furnace. Everything known about physics said that the radiation should behave like a smooth, continuous flow, a wave. But the calculations done with the wave theory didn't match observation.
Planck began to think about it, and he saw that you could get round this. The calculations were wrong because they were assuming that the radiation was behaving just like smooth flow, like the flow of water from a tap. He saw that, in fact, the radiation was not behaving that way. It was coming in drips, as you might say, in packets, one at a time. One packet of energy followed by another packet of energy. These packets consisted of so much energy, and so it was a quantum of energy, so much of energy, and that's where the name quantum and quantum theory comes from.
Planck's quantum theory suggested the seemingly impossible. Light could be both a wave and a particle. It was so impossible that Planck stopped short of saying so.
He found that you could only explain the way light comes out of atoms, the spectrum of light, in terms of little packets of energy coming out. But he never suggested that the light only existed as little packets of energy. And the analogy I like to use is with a cash dispenser at a bank. If you go to the cash dispenser at my bank, you can get money out in multiples of £5, but there's no way you can get £4 out because it can't give you coins, it can only give you notes.
The leap of imagination came from a young patent clerk who in 1905 dared to think the unthinkable.
Einstein said, it's the light itself that only exists in lumps of a certain size.
Einstein reinforced the concept that light had a particle character. The whole of 19th century physics has shown that it had a wave-like character, so the physicists today were left with this intolerable paradox, really, that sometimes light looked like waves, sometimes like particles. And I think it's fair to say that most of them were so upset by this, they swept it under the carpet and said, we won't bother about that. But of course, some people persisted, and through their persistence, modern quantum theory eventually was discovered.
The revolution in physics would have to wait for more urgent matters to be resolved. By the end of the Great War, a new generation was now ready to question the established order. Physics was no exception. The catalyst for change was a young French aristocrat, Prince Louis de Broglie.